In the vast dark between stars, where distances are so large they lose any familiar meaning, astronomers rely on a strange idea to make sense of it all. A unit that sounds like time, but measures space. A phrase spoken casually, yet carrying more distance than the human mind was ever designed to hold. The light year. Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations. And if you feel like it, share where in the world you're listening from tonight. It is always grounding to know how far these thoughts travel. At first glance, the term light year feels simple. Light moves quickly, a year passes slowly. Combine the two, and the meaning seems straightforward. Yet beneath that simplicity lies something deeply unintuitive, a distance defined not by steps, roads, or maps, but by motion itself, by the steady movement of light across an expanding universe, carrying information from places so remote that their scale resists imagination. For centuries, distance meant something physical. How far a journey felt, how long it took to walk. Later, how many days by ship, or hours by train. Even now, distance is often tied to effort and time. But space does not cooperate with those instincts. Beyond Earth, kilometers stretch thin. Beyond the solar system, they collapse entirely. Numbers grow so large they stop conveying meaning and begin to blur into abstraction. The light year emerged not as a poetic invention, but as a practical necessity, a way for astronomers to describe separation without drowning in zeros, a way to talk about stars, galaxies, and cosmic structure, using the one thing that moves reliably through the vacuum of space, light itself. Tonight's journey is not about memorizing figures or racing across cosmic scales. It is about slowly approaching an idea that feels familiar on the surface, yet becomes stranger the longer it is held. What it truly means to say that something is light years away. Why that distance feels so different from anything experienced on Earth, and how this single unit quietly reshapes the way the universe is understood. Settle in, let distance stretch gently, and allow the question to unfold at its own pace. How far is a light year really? Distance feels intuitive on Earth because it was learned slowly, through bodies that walk, eyes that judge depth, and lives that unfold at human speed. A few steps across a room, a short walk to a nearby street. A longer journey that takes an afternoon, a day, or perhaps a week. These are distances shaped by muscle, breath, and patience. They are distances that can be felt in tired legs, and measured in familiar units that still mean something when spoken aloud. Human intuition formed in this narrow range. Evolution had no reason to prepare the mind for emptiness stretching millions of times farther than the horizon. Survival depended on judging whether a jump could be made, whether a shelter was close enough to reach before nightfall, whether food was within a manageable radius. Distance was personal, it was immediate. It was tied to effort and consequence. Even as technology expanded that range, intuition lagged behind. Car journeys compress hundreds of kilometers into a single afternoon, yet the experience still unfolds as a sequence of landmarks, pauses, and moments of waiting. Flights shrink continents to a few hours, but they remain wrapped in familiar sensations of movement and arrival. No matter how fast travel becomes, the distances remain anchored to human schedules and human bodies. Space does not offer that anchor. Beyond Earth, distance disconnects from effort almost immediately. The moon, close enough to see clearly with the naked eye, lies far enough away that even at the speed of a jet aircraft it would take weeks to reach. Light, moving faster than anything else in the universe, still needs a little over 1 second to cross that gap. Already intuition begins to slip. Stretch that distance to the sun, and the numbers become harder to hold. Sunlight takes a little more than 8 minutes to arrive at Earth. That means the warmth felt on the skin began its journey while breakfast was still being made or while a kettle was still heating. This delay is small enough to sound trivial, yet large enough to quietly disrupt the idea of immediacy. The sun is not where it appears to be. It is always seen slightly in the past. Move outward again, past the orbit of the outer planets, and kilometers and miles start to lose their grip entirely. These units were designed for roads, maps, and borders. They work beautifully when distance can be crossed, even slowly. In space, they inflate into strings of digits that convey precision without meaning. Saying that something is billions of kilometers away communicates accuracy, but not understanding. The mind hears the number, nods politely, and then lets it drift away. This is where the strangeness truly begins. Space demands a different way of thinking, one that replaces movement with waiting. Instead of asking how long it would take to travel somewhere, astronomers ask how long light takes to arrive. Distance becomes something passive, not a journey to be made, but a message already in transit. This shift is subtle, yet profound. On Earth, distance is something that can usually be shortened. Faster vehicles, straighter roads, better planning. In space, distance is not waiting to be overcome. It simply exists, indifferent to ambition. Even the fastest spacecraft ever launched would take tens of thousands of years to reach the nearest stars. At that scale, travel stops being a realistic concept and becomes a thought experiment. The brain resists this idea instinctively. It wants motion, progress, arrival. It wants to imagine drifting forward, slowly but surely, until a destination appears. Space offers drifting without arrival. Waiting without change. A calm, unbroken separation that does not care whether it is being crossed at all. Scientific institutions that study space are well aware of this cognitive mismatch. Astronomers and physicists often describe distance using layered metaphors, not because the science is unclear, but because human intuition needs help. Organizations like national space agencies routinely explain cosmic scales by compressing them into familiar comparisons, even while knowing those comparisons will eventually fail. The numbers can be written down precisely, but precision does not guarantee comprehension. What makes this even stranger is that space is mostly empty. Between planets, between stars, between galaxies, there's very little to mark progress. On Earth, distance is broken up by terrain, buildings, trees, and horizons. In space, there are no such cues. One can drift for millions of kilometers and see nothing change at all. The absence of landmarks strips distance of texture. It becomes smooth, silent, and difficult to sense. This emptiness plays tricks on perception. Two stars that appear side by side in the night sky may be separated by hundreds or thousands of light years. They look close because vision collapses depth when scale exceeds experience. The mind assumes proximity where none exists. Space turns depth into illusion. Walking offers a useful contrast. When walking, distance unfolds one step at a time. The body counts progress automatically. Muscles tighten and relax. Breathing adjusts. The environment responds. Even waiting has texture on Earth. Waiting for a train, waiting for a message, waiting for daylight. There are sounds, movements, small changes that mark time passing. Waiting in space is different. Light leaves a distant star and moves steadily outward, uninterrupted. Nothing nudges it along, nothing slows it down. It simply travels, carrying information across distances that were already vast before it began. When that light finally arrives, the event it represents may have happened long before the listener ever existed. This is why distance in space feels so strange. It is not just larger than expected, it behaves differently. It disconnects cause from effect. It separates seeing from happening. It replaces motion with transmission and travel with patience. Scientists studying cosmic scale often point out that the universe operates comfortably at distances that make human life seem momentary, not insignificant, but brief. Observations collected by space telescopes reveal structures stretching across hundreds of thousands of light years, shaped slowly by gravity over spans of time that dwarf recorded history. These facts are not meant to diminish human experience, but they do challenge the instinctive belief that distance must always be relatable. There is gentle humour in this mismatch. The same species that struggles to visualize 1,000,000 kilometers can calculate the expansion of the universe with extraordinary accuracy. Equations describing motion and gravity work flawlessly at scales intuition cannot reach. Understanding does not require feeling. Knowledge does not require comfort. In this way, space invites a quieter relationship with distance, one that replaces urgency with acceptance. Walking gives way to drifting. Waiting becomes a feature, not a flaw. Distance stops being something to conquer and becomes something to acknowledge. When kilometers and miles fall away, something else takes their place. A sense that distance is not about how far something is, but about how long information takes to arrive. A recognition that seeing is always delayed and that the universe is never experienced in real time. This strange arrangement is not an error in perception. It is a consequence of living in a universe where light has a finite speed and space has no obligation to be small. Once that is accepted, distance begins to feel less hostile and more like a quiet constant. Always present, always stretching, always waiting. Light is so familiar that it almost disappears into the background of experience. It fills rooms, reflects off surfaces, and quietly delivers the colours, shapes, and motion that make the world readable. Eyes open, and light is already there, doing its work without announcement. Because of that familiarity, it is easy to forget that light is not a substance in the everyday sense. It is not a stream of particles flowing like water, nor a static glow that simply exists in place. Light is a form of electromagnetic radiation, a travelling disturbance that moves through space carrying energy and information. That phrase can sound technical, but the idea itself is gentle. Light is a ripple, not a ripple in air like sound, and not a ripple in water like a wave in a pond, but a ripple in invisible fields that exist everywhere in the universe. These fields are part of the structure of reality itself. When light is produced by a star, a lamp, or a candle flame, it sends a tiny oscillation outward, spreading through space in all directions. One of the remarkable features of light is that it does not need a medium to travel. Sound requires air. Waves on the ocean require water. Light moves perfectly well through empty space. This is why sunlight crosses the vast vacuum between the sun and earth without difficulty. It is also why the darkness between stars is not an obstacle, but simply the absence of light sources. Physicists discovered long ago that light behaves with extraordinary consistency. No matter where it is produced, no matter how empty or crowded the space around it, light travels at the same maximum speed. This speed is not merely very fast. It is woven into the structure of the universe itself. Nothing that carries information can move faster. The approximate speed of light is often quoted as about 300,000 kilometers per second. Spoken aloud, that number sounds impressive but abstract. What matters more than the figure itself is what it represents. Light moves so quickly that it can circle the Earth several times in a single second. It can travel from the Moon to Earth in a little over 1 second. Yet even at this extraordinary pace, distance still matters. What makes light truly strange is that its speed does not change depending on motion. If a light source is moving, the light it emits still travels at the same speed. If an observer is moving toward the light or away from it, the measured speed remains unchanged. This constancy was confirmed through careful experiments and is now one of the most tested facts in all of physics. It feels counterintuitive because it clashes with everyday experience, where speeds usually add and subtract. Light does not play by those rules. This fixed speed gives light a special role. It becomes a universal clock of sorts, a way to link distance and time in a consistent, reliable manner. When light leaves a source, the time it takes to arrive somewhere else tells a story about how far it has travelled. Distance becomes something that unfolds second by second, quietly and steadily. Scientists often explain this by pointing out that every beam of light carries a timestamp, not a written label, but an implied one. The moment the light was emitted is encoded in how long it takes to reach an observer. When sunlight warms the skin, it is sunlight that began its journey a little over 8 minutes earlier. When starlight enters a telescope, it may have left its source years, centuries, or far longer ago. This connection between light, distance, and time is not a poetic metaphor. It is a practical tool used by astronomers every day. Because light speed is constant, it becomes a ruler that stretches naturally across space. Each second of travel corresponds to a fixed amount of distance. Each year of travel corresponds to an enormous span. The idea that light has a maximum speed was once deeply unsettling. At the beginning of the 20th century, experiments showed that no matter how motion was measured, the speed of light refused to change. This puzzled scientists until new theories emerged explaining that space and time themselves adjust to preserve this limit. The universe, it turned out, is built around light's behaviour, not the other way around. Institutions dedicated to studying space rely on this principle constantly. Space agencies use light signals to communicate with distant spacecraft, timing how long messages take to travel. Astronomers measure distances to stars by comparing tiny shifts in position caused by Earth's motion, knowing exactly how light must behave. The consistency of light speed underpins everything from satellite navigation to deep space observation. There is a quiet elegance in this arrangement. Light does not rush even though it moves incredibly fast. It does not slow down even when space stretches vast and empty. It simply travels steadily, indifferent to what lies along its path. In doing so, it links places that would otherwise remain isolated by unimaginable distances. Gentle humour sometimes appears in how scientists talk about light. It is often described as stubborn. No matter how cleverly experiments are designed, light refuses to cooperate with everyday expectations. Try to chase it, and it still pulls away at the same pace. Try to measure it from different frames of reference, and it calmly gives the same answer every time. This reliability is precisely why light becomes such a powerful measuring tool. Distance over time becomes not an abstract idea, but a physical process unfolding in real space. Light leaves, light travels, light arrives. The interval between those moments defines separation in the universe more faithfully than any ruler ever could. Understanding light this way also changes how distance is perceived emotionally. Distance is no longer just space to be crossed. It is time already spent. When something is said to be far away, it is also old, in a very literal sense. The light reaching an observer has been travelling, uninterrupted since long before the moment of observation. Seen this way, space becomes less about emptiness and more about continuity. Light stitches the universe together, 1 second at a time. Every point in space is connected by streams of radiation moving outward, carrying stories of their origins. This is the foundation upon which larger ideas of cosmic distance are built. Before kilometers lose meaning, before planets and stars spread beyond imagination, light quietly establishes the rules. It sets the pace. It defines the relationship between separation and duration. And it does so with remarkable calm, never hurrying, never slowing, always moving at exactly the same speed through the dark. For most of human history, distance in the sky was not something that could be measured in any practical sense. The stars appeared fixed, evenly spaced on a vast dome, changing only with the seasons. They rose, they set, and they returned night after night with reassuring regularity. To early observers, the heavens were a pattern, not a place. Distance existed there, but it had no depth. The first real attempts to measure astronomical distance stayed close to home. Within the solar system, careful observation could turn motion into measurement. Ancient astronomers noticed that nearby objects, like the moon or the planets, shifted slightly against the background of more distant stars as Earth moved. This effect, later called parallax, allowed the nearest distances in space to be estimated with surprising accuracy. By watching how the moon appeared to shift from different locations on Earth, its distance could be calculated. The same idea applied to the sun, although that required far more patience and precision. By the time of early modern astronomy, scientists had begun to assemble a rough map of the solar system, using geometry, timing, and observation. Distances were expressed in kilometers or miles, the same units used on Earth, just stretched a little farther than usual. At first this worked well enough. The moon sits comfortably within a few 100,000 kilometers. The sun lies about 150 million kilometers away. Even the outer planets, while distant, could still be described using familiar units, without completely overwhelming the imagination. The numbers were large, but not yet absurd. Then the edges of the solar system came into view. As telescopes improved, astronomers began to understand just how much empty space lay between the planets. Distances multiplied quickly. Neptune, the most distant major planet, orbits billions of kilometers from the Sun. Already the figures were starting to feel unwieldy. Saying them aloud took time. Writing them down required strings of zeros that conveyed more fatigue than meaning. And this was still only the local neighborhood. Once astronomers turned their attention beyond the solar system, the problem became impossible to ignore. The nearest stars were found to be unimaginably far away. Not millions of kilometers, not billions, trillions. Numbers so large that even careful scientists hesitated before speaking them, knowing that accuracy did not guarantee understanding. Traditional units had reached their breaking point. Kilometers and miles, so useful for roads and orbits, were never designed for interstellar space. They demanded too many digits. They cluttered explanations. They slowed conversation. Each attempt to describe distance became an exercise in endurance. There was nothing wrong with these units mathematically. They were precise. They were well defined. But they were no longer practical. And astronomy, despite its grand subject matter, has always been a deeply practical science. Observations must be recorded clearly. Measurements must be shared. Ideas must be communicated without drowning in notation. This is where light quietly stepped in. Astronomers were already thinking in terms of light without fully realizing it. Telescopes collect light. Observations are delayed by the time light takes to travel. Every image is a message from the past. Distance and light were already intertwined in practice, even if the language had not yet caught up. The idea emerged gradually and almost reluctantly. Instead of asking how many kilometers separate 2 points in space, why not ask how long light takes to travel between them? Light moves at a constant speed. It does not slow down. It does not take shortcuts. It provides a built-in connection between time and distance that works everywhere in the universe. This was not an attempt to be poetic or clever. It was an attempt to stay sane. Using light as a measuring stick meant that distances could be expressed in terms that carried immediate meaning within astronomy. A star several light years away is not just far. It is far in a way that directly relates to observation. The light being seen left that star several years ago. The distance and the delay are the same thing. This shift simplified conversation enormously. Instead of reciting enormous numbers, astronomers could speak in units that reflected how the universe is actually experienced. Light years did not replace kilometers because kilometers were wrong. They replaced them because kilometers had become inconvenient. Scientific organizations quickly adopted this approach because it worked. Observatories reporting stellar distances found that light-based units allowed results to be compared more easily. Calculations became clearer. Explanations became shorter. The science did not change. The language did. There is gentle humor in how quickly numbers can lose their dignity. A distance described as several trillion kilometers may be accurate, but it does not invite intuition. It sits on the page like an uninvited guest. Convert that same distance into a few light years, and suddenly it fits comfortably into a sentence. Even within professional astronomy, this practical advantage matters. Research papers, lectures, and discussions all benefit from units that reduce clutter. When numbers become ridiculous, clarity suffers. Light-based units trim the excess without sacrificing precision. It's worth noting that astronomers did not abandon older units entirely. Within the solar system, kilometers and astronomical units remain useful. An astronomical unit, defined as the average distance between Earth and the Sun, provides a convenient middle ground. It keeps numbers manageable without introducing unnecessary abstraction. But beyond the solar system, light-based measurements reign. Stars, clusters, and galaxies are naturally described in terms of how long their light has been travelling. This aligns measurement with reality. It acknowledges that observation itself is limited by the speed of light. The adoption of light as a ruler also reflects a deeper acceptance. Space is not something that can be crossed casually. It is something that must be weighted through. Measuring distance by light travel time quietly reinforces that truth. Every large distance implies patience. Every observation carries delay. There is something calming about this perspective. Instead of fighting the vastness of space with ever larger numbers, astronomers chose to describe it using a constant that behaves beautifully and predictably. Light becomes the mediator between places that will never be reached directly. This approach has been refined and standardized by scientific institutions around the world. Space agencies, observatories, and international astronomical organizations all rely on light-based units when dealing with deep space. It is not a stylistic choice, it is a practical one, born from necessity. In the end, the need for a new unit did not arise because the universe changed. It arose because understanding expanded. The moment astronomy stepped beyond the solar system, familiar tools began to creak under the strain. Light offered a solution that was already present, already reliable, and already essential to observation. When distances grew too large for kilometers to behave themselves, light quietly took over. Not to impress, not to confuse, but to keep the conversation going. A light year sounds, at first, like it should be a measure of time. The word year sits there so confidently that the mind almost refuses to see anything else. This is why the term causes so much quiet confusion. It asks distance to borrow the language of duration, and in doing so it gently rewires how scale is understood. A light year is the distance that light travels in 1 year. That is the entire definition. Nothing more is hiding behind it. No trick, No poetic flourish, simply the path light covers as it moves steadily through space for the length of a year. The reason this works begins with something already established. Light travels at a fixed speed. It does not matter where it comes from or who is observing it. Because that speed is constant, time becomes a reliable way to measure how far light goes. 1 second of travel always corresponds to the same distance. 1 minute always covers more ground. 1 year covers an enormous amount of space. This is why time appears in the definition at all. It is not because distance is somehow turned into time. It is because light provides a bridge between the two. Time is the handle humans can comfortably grasp. Distance at cosmic scales is not. When astronomers speak of a light year, they are really saying, this is how long light had to travel to get here. The distance is implied by the journey. The year is not a clock reading. It is a ruler that unfolds second by second as light moves forward. If a single numerical figure must be mentioned, it can be stated calmly and then set aside. 1 light year is roughly 9.5 trillion kilometers. That number is accurate. It is also deeply unhelpful if repeated too often. The brain hears it, acknowledges it, and then politely lets it go. This is precisely why astronomers rarely use that figure in everyday discussion. Saying 9.5 trillion kilometers does not build intuition. It builds fatigue. It turns conversation into accounting. The number becomes the focus rather than the relationship it describes. Using a light year keeps attention where it belongs, on the idea of separation, on the fact that light has been travelling uninterrupted for a full year. That alone already conveys vastness more effectively than any string of digits ever could. There's also something quietly honest about this definition. It does not pretend that distance is something easily crossed. It acknowledges that even light, the fastest messenger in the universe, needs time. A light year carries patience built into its meaning. This is why memorization is not the goal. No one needs to recall the exact number of kilometers in a light year to understand what it represents. Understanding comes from recognizing that light has been moving continuously for a year without stopping. That image does far more work than arithmetic ever could. Scientific organizations that define and standardize measurements are careful about this distinction. They emphasize clarity over memorized figures. The point is not to impress with scale, but to communicate it accurately. When distances are described in light years, the listener immediately knows that time and separation are intertwined. The definition also avoids a common misunderstanding. A light year is not how long something takes to happen. It is not a countdown. Nothing special occurs at the end of the year. Light does not arrive and celebrate its anniversary. The year is simply a convenient duration, familiar enough to feel grounded, long enough to be useful. There is gentle humour in how stubborn this misunderstanding can be. Even people deeply interested in space sometimes catch themselves thinking of light years as time. The phrase invites it. But once the definition settles in, the confusion usually fades. The term begins to feel natural, even elegant. Another reason the number itself is rarely used is that it scales beautifully without it. Half a light year, several light years, thousands of light years. These phrases retain meaning without requiring mental arithmetic. They keep the focus on relative distance rather than absolute magnitude. Astronomers rely heavily on this flexibility. When discussing nearby stars, a few light years feels close in a cosmic sense. When describing galaxies, tens of thousands of light years feels appropriate. The unit stretches smoothly across scales without demanding recalculation. This is part of its quiet success. A light year adapts to context. It does not insist on precision where precision adds nothing. It allows distance to be discussed fluidly in ways that match how the universe is observed. There is also an important emotional aspect to this definition. Distance measured in light years automatically carries history. If something is 100 light years away, the light arriving now began its journey a century ago. That fact is not an added detail. It is built into the measurement itself. This does not mean the object is frozen in the past. It means observation is delayed. The light year gently reminds the listener that seeing is not the same as knowing the present. In astronomy, everything is slightly out of date. This perspective can be unsettling at first, but it also brings calm. It removes urgency. The universe is not racing. It unfolds at a pace set by light, and that pace is fixed and dependable. Defining a light year clearly also helps avoid exaggeration. Space is vast, but it is not vague. Distances are enormous, but they are measured carefully. The light year keeps that balance. It acknowledges scale without turning it into spectacle. Real scientists often emphasize this point when teaching or communicating astronomy. The goal is not to overwhelm, it is to build intuition slowly. A light year works because it connects an unfamiliar distance to a familiar duration, without pretending they are the same thing. Understanding, in this case, comes from letting the idea settle, rather than forcing it to stick. The definition does not need repetition, it needs space. Once the mind accepts that light moves for a year and ends up somewhere else, the meaning is already there. The term also quietly reinforces something deeper about the universe, that there is a speed limit. That information takes time. That separation is not just about where things are, but about when they can be known. A light year is not a number to memorize. It is a relationship to understand. Light moves, time passes, distance accumulates. That is all. And once that is clear, the phrase begins to feel less strange. It becomes a calm, practical way to talk about a universe that does not scale down easily, but does explain itself patiently, 1 year of light at a time. Trying to understand the distance of a light year often begins with translation. The mind reaches for Earth-based experience and asks how that enormous stretch of space might feel if it were walked, driven, or flown. These comparisons are not mistakes. They are the only tools intuition has. But when real numbers are allowed to stay in the room a little longer, those tools begin to show their limits gently, rather than dramatically. Begin with walking, the slowest and most human measure of distance. A typical walking speed is about 5 kilometers per hour. At that pace, a person might cover 40 kilometers in a long day of steady effort. That is enough to cross a city or move between neighboring towns. Over a year of uninterrupted walking, assuming no rest days and no need for sleep, roughly 40,000 kilometers could be covered. That is just enough to circle Earth once. A light year, by contrast, is about 9.5 trillion kilometers. At walking speed, covering that distance would take well over 200 billion years. That is more than 10 times the current age of the universe, which astronomers estimate at roughly 13.8 billion years based on measurements of cosmic expansion and background radiation. Long before even a fraction of that journey could be completed, stars would be born and die. Galaxies would shift their shapes, and Earth itself would no longer exist in its current form. Driving improves the numbers, but not the outcome. A typical highway speed might be 100 kilometers per hour. At that pace, a car could travel about 876,000 kilometers in a year of continuous motion. That sounds impressive until it is placed beside a light year. At that speed, the journey would still take more than 10 million years. That is longer than the entire history of modern humans as a species. Flying feels faster still. A commercial jet travels at roughly 900 kilometers per hour. Over a year of non-stop flight, that adds up to just under 8 million kilometers. Against a light year, the difference between walking and flying becomes surprisingly small. Both barely register. At jet speed, the journey would take over 1 million years. Even the most extreme examples of human travel struggle to matter. The fastest aircraft ever built reached speeds of several thousand kilometers per hour. Even at those speeds, reaching a single light year would still require hundreds of thousands of years. Spacecraft do better, but not nearly well enough to change the story. The fastest human-made objects, such as deep space probes launched by international space agencies, travel at tens of kilometers per second. One well-known probe is moving at roughly 17 kilometers per second relative to the Sun. That is about 60,000 kilometers per hour. At that speed, the probe travels roughly 500 million kilometers per year. That is enough to cross the distance from Earth to the Sun several times over. It is enough to leave the solar system entirely. Yet even at this remarkable pace, reaching 1 light year would take close to 18,000 years. After more than 40 years of travel, such probes have covered only a few hundredths of a light year. This is not a limitation of ambition or intelligence. It is a direct consequence of scale. Astronomers are careful when presenting these figures, not because they are uncertain, but because piling numbers too quickly can blur meaning. Still, allowing a few of them to settle helps clarify perspective. A light year is not just bigger than Earth-based distances. It is larger by factors that overwhelm linear comparison. Another way to approach this is through Earth's size itself. Earth has a diameter of about 12,700 kilometers. Roughly 700 Earths placed edge to edge would span the distance from Earth to the Sun. That sounds vast until it is extended outward. Nearly 63,000 Earth diameters would fit inside the distance light travels in a single hour. Nearly 9.5 trillion Earth diameters would fit inside a light year. These comparisons are not meant to shock, they are meant to loosen the grip of familiar scale. What matters more than any single figure is how quickly progress stops feeling like progress. On Earth, doubling speed meaningfully reduces travel time. In interstellar space, doubling speed often changes nothing about feasibility. The numbers remain too large. This is why astronomers rarely frame interstellar distances in terms of vehicles. Space agencies do not plan missions to nearby stars using current propulsion, because the timelines stretch beyond any practical horizon. Instead, they focus on observation. Light does the travelling instead. Light covers 1 light year in 1 year because that is how the unit is defined. It travels at about 300,000 kilometers per second, which means it covers nearly 10 trillion kilometers in 12 months. That number appears once and then steps back. Its role is not to be memorized, but to anchor understanding. Compared to Earth-based travel, light behaves almost differently from motion. It does not need fuel. It does not accelerate or decelerate. It does not experience wear. It simply moves. This contrast highlights an important shift in perspective. Earth-based distances are tied to effort. Interstellar distances are tied to time. Asking how far a light year is compared to Earth is really asking how long the universe is willing to wait. Even when Earth-based metaphors are stretched to their limits, they eventually dissolve. Walking, driving, and flying all depend on surfaces, engines, and destinations. Space offers none of these comforts. There is nothing to push against, nothing to mark progress, nothing to arrive at until arrival is complete. Astronomers often stress that this does not make Earth small in a dismissive sense. It makes Earth specific. Planetary distances are meaningful within planetary contexts. Human travel is extraordinary within human domains. The problem only arises when one scale is expected to behave like another. A light year gently refuses that expectation. By increasing the factual detail, the picture becomes clearer without becoming louder. The numbers do not demand awe. They invite orientation. They show that the universe is not built to be crossed quickly, and that this is not a flaw. Ending with that understanding brings a quieter response than shock ever could. A light year is far, not because humans are slow, but because space is vast. Earth-based travel barely registers against it, not as an insult but as a reminder. Perspective settles in. The figures stop racing. Distance becomes something to recognize rather than challenge. And in that recognition, there is room for calm, accuracy, and a steady sense of place within a universe that moves at its own pace. Inside the solar system, light years quietly step aside, not because they are wrong, but because they are far too large for the space they would be asked to describe. Using light years to measure distances between planets would be like using continents to describe the size of a room. The scale works mathematically, but it obscures rather than clarifies. The solar system is vast by human standards, yet small by cosmic ones. Distances here are better understood through shorter measures of light travel time. Light seconds and light minutes offer a scale that fits comfortably with what is actually happening between the Sun, the planets, and the spacecraft exploring them. Light seconds are often the first step. Light travels fast enough to circle Earth several times in a single second, yet even that speed encounters noticeable delays within our own planetary neighbourhood. The Moon, for example, sits about 1 light second away. When astronauts spoke from the lunar surface, there was a brief pause before their voices reached Earth. That pause was not a technical problem. It was distance, made audible. Stretch the distance a little farther, and light minutes come into play. Sunlight takes a little over 8 minutes to reach Earth. This means that the sun seen in the sky is not the sun as it exists right now, but as it was a few minutes ago. If the sun were to vanish at this moment, Earth would continue basking in sunlight for those remaining minutes, unaware that anything had changed. This fact is often mentioned because it feels surprising, but it also serves as a gentle introduction to how light travel time shapes perception. 8 minutes is short enough to imagine, yet long enough to matter. It is the length of a brief walk, a cup of tea, a moment of waiting. In those everyday spans of time, light has crossed 150 million kilometers of space. Other planets extend this delay further. Light from the Sun reaches Mars in a little over 12 minutes on average, depending on where the two planets are in their orbits. When Mars is farther away, that delay stretches to over 20 minutes. Jupiter sits much farther out. Sunlight takes more than 40 minutes to reach it. Saturn pushes that delay to well over an hour. These numbers remain manageable because they stay anchored to time spans that feel real. Minutes and hours can be weighted through. They can be marked by clocks. They can be imagined as periods of quiet delay rather than abstract distance. This way of thinking becomes especially important when communicating with spacecraft. Signals sent to probes exploring the outer solar system do not travel instantly. They move at the speed of light, and even that introduces noticeable lags. When mission controllers send a command, they must wait for the signal to arrive. Then they must wait again for confirmation to return. For spacecraft near Mars, this round-trip delay can be anywhere from several minutes to nearly 40 minutes. Engineers plan carefully around this limitation. They do not steer probes in real time. They send instructions in advance, knowing that by the time a response arrives, the situation may already have changed. For probes much farther away, the delays become longer still. Spacecraft that have passed beyond the outer planets experience communication delays of many hours. A signal sent today may not be acknowledged until later the same day or even the next. This is not a flaw in technology. It is the natural consequence of distance inside the solar system. Space agencies design missions around these delays from the very beginning. Autonomous systems are built into spacecraft so they can respond to conditions without waiting for instructions from Earth. Light travel time shapes how exploration itself is carried out. Using light seconds and light minutes keeps this reality clear. It reminds listeners that even within our local region of space, immediacy is an illusion. Information takes time to move. Cause and effect are separated by quiet intervals. This also helps explain why light years are unnecessary here. A light year is simply too coarse a unit. The entire solar system, from the Sun to its most distant boundary of gravitational influence, spans only a tiny fraction of a light year. Expressing these distances in light years would require awkward decimals that hide more than they reveal. Instead, astronomers often use astronomical units, or light minutes. An astronomical unit is defined as the average distance between Earth and the Sun, about 150 million kilometers. Light minutes translate that same distance into time. Both approaches work. Light minutes simply make the delay explicit. There is gentle humor in how quickly the scale changes. 8 minutes feels trivial until it becomes a hard limit on communication. 40 minutes feels manageable until it stretches decision-making across half an afternoon. Hours feel long when waiting for a reply from a machine billions of kilometers away. Even so, the solar system remains close by cosmic standards. The entire region that light crosses in hours would take light years to traverse between stars. This contrast is not meant to diminish the solar system, but to place it accurately. Near does not mean small. Nearby space is still enormous. Planets are separated by distances that would swallow Earth whole many times over. Empty space dominates. Motion is slow. Waiting is constant. Scientists studying planetary systems emphasize this point often. The solar system may feel compact when drawn on diagrams, but those diagrams are necessarily compressed. If distances were drawn to scale, planets would vanish into dots separated by long stretches of nothing. Light seconds and minutes help restore some of that spacing. Understanding this prepares the mind gently for larger scales. It shows that even before reaching interstellar space, the universe already refuses instant connection. The speed of light, while fast, does not erase separation. It simply defines it. This perspective also reframes the idea of closeness. Earth and the Sun are close in an astronomical sense, yet still separated by minutes of light travel. Earth and the Moon are neighbours, yet still divided by seconds. These delays are not inconveniences, they are measurements of space itself. By keeping light years out of the solar system, astronomers preserve clarity. They choose units that fit the situation. Light seconds for nearby worlds, light minutes for planetary distances, light years for stars. Each scale has its language. In this way, the solar system becomes a training ground for understanding distance. It teaches patience without overwhelming. It introduces delay without abstraction. It shows that even the space called home is vast, quiet, and structured by light moving steadily through emptiness. By the time light years finally appear, they arrive not as a shock, but as a natural extension. The lesson has already been learned. Distance is time, near is relative, and even the spaces considered familiar are far larger than they first appear. Once the idea of light years settles into place, attention naturally drifts outward, away from the Sun and its planets, toward the nearest stars. This is often where the scale of space quietly changes character. Within the solar system, distances felt large but still connected. Between stars, distance becomes separation. The stars closest to Earth are described as nearby, but that word carries a very different meaning here. Nearby does not mean reachable. It does not mean close in any everyday sense. It simply means closer than everything else. The nearest stars lie several light years away. That means the light arriving now began its journey years ago, moving steadily through empty space without interruption. Even the closest stellar neighbours are not just distant in kilometres, but distant in time. To put that gently into human terms, imagine a message sent without reply. A letter written, sealed and released, knowing that no response could arrive for years. Not because the recipient is uncooperative, but because space itself insists on patience. That is what a few light years represent. Not drama, just delay. This delay is not theoretical. Astronomers measure it directly. Light from nearby stars takes years to reach Earth. When telescopes collect that light, they're recording conditions from the past. The stars may have changed slightly since then, but those changes have not yet arrived. Scientists often emphasize that nearby stars are not clustered together. They are spread out through space, separated by vast, quiet intervals. If the Sun were placed alone in a dark volume, the nearest stars would still feel uncomfortably far away. Space between stars is not crowded. It is sparse. Human intuition struggles here because it expects continuity. On Earth, moving a short distance usually reveals something new. Another building, another hill, another town. In space, moving the same relative distance reveals nothing at all. The emptiness persists. Even when numbers are introduced, they remain surprisingly unhelpful without context. Saying that a nearby star is several light years away is accurate, but the meaning lives in what that implies. Several years of uninterrupted light travel. Several years during which nothing slows the signal. Several years of silence between emission and arrival. If a spacecraft travelling at the fastest speeds humans have achieved were aimed toward one of these nearby stars, it would require tens of thousands of years to arrive. Entire chapters of human history would unfold while the craft moved only a small fraction of the way. This is not a limitation of design. It is a reflection of scale. Astronomers sometimes illustrate this by pointing out that if the solar system were reduced to the size of a coin, the nearest stars would still be many kilometers away. This comparison is not meant to impress. It is meant to clarify how empty space really is. Isolation becomes the dominant feature at this scale. Stars are not neighbours in the way houses are neighbours. They do not form continuous landscapes. Each star carries its own planetary system, surrounded by vast regions where nothing much happens at all. This isolation is stable. Stars do not rush toward each other. Their motions are slow, governed by gravity across enormous distances. Even over millions of years, their relative positions change only gradually. The universe is not bustling at this level. It is drifting. From a scientific perspective, this isolation is important. It allows astronomers to study stars as individual systems. Their light arrives largely uncontaminated by nearby sources. Each star tells its own story, carried across years of space. Real-world scientific institutions rely on this separation to make precise measurements. Telescopes can isolate starlight, analyze its spectrum, and infer temperature, composition, and motion. The distance implied by light years becomes part of that analysis, not as an obstacle, but as a known factor. There is gentle humour in how language adapts here. The phrase nearby star sounds friendly, almost casual. In reality, nearby means unimaginably far. The words remain calm while the scale quietly stretches beyond experience. This calm is important. Emphasizing drama would miss the point. The distance to nearby stars is not frightening. It is simply spacious. It reflects a universe built with room to spare. Understanding this also helps dissolve certain expectations. Science fiction often compresses stellar distance into something navigable. Ships travel between stars as if crossing oceans. While imaginative, this framing hides the real lesson. Stars are isolated not by hostility, but by scale. The separation between stars means that each system evolves largely on its own. Planetary systems form, mature, and change without constant interference. Light becomes the primary connection. Information travels, but slowly. Influence spreads, but gently. When astronomers speak of the local stellar neighborhood, they're referring to a region that still spans many light years in every direction. Even within this neighborhood, stars are separated by distances that would feel enormous by any Earth-based measure. This perspective encourages patience. It suggests that the universe is not arranged for quick exchange. It favors stability over speed. Change occurs, but it takes time to arrive. Human terms help here, as long as they are used carefully. Waiting years for light to arrive is not something experienced directly, but waiting days or months for news offers a faint echo. Multiply that waiting far beyond comfort, and the scale begins to take shape. There is also a quiet reassurance in this isolation. Distance provides space for complexity to develop independently. It prevents overcrowding. It allows stars and their planets to exist without constant disruption. Astronomers studying stellar populations often note that this spacing is not accidental. It emerges naturally from how matter collapses and spreads under gravity. Stars form where material gathers, but the gathering leaves wide gaps behind. These gaps are not empty in an absolute sense, but they are empty of landmarks. Light travels through them without obstruction. Time passes without notice. Distance accumulates without resistance. In this environment, light years become the most natural way to speak. They describe not just how far away something is, but how long the universe has been carrying its message. A nearby star measured in light years is not just distant, it is delayed. This delay is not a problem to solve, it is a condition to understand. By emphasizing isolation rather than drama, the picture becomes clearer. Stars are not unreachable fortresses, they are simply far apart. The universe does not compress itself for convenience. It unfolds according to its own scale. Once this is accepted, nearby stars stop feeling deceptively close. They take their proper place as distant companions, visible but separate, connected by streams of light moving patiently through darkness. The distance between stars is not a barrier, it is a feature, one that gives the universe its quiet, open character. And in that openness, the idea of a light year feels less like an abstraction and more like an honest description of how space truly works. When distance is measured in light years, something subtle but important happens to perception. Space quietly turns into time. Looking farther away no longer means simply looking across emptiness. It means looking backward. Not metaphorically, not imaginatively, but physically and unavoidably. This idea often sounds like science fiction at first, as if telescopes were time machines pointed into the past. In reality, nothing so dramatic is taking place. There is no bending of timelines or glimpses of alternate histories. There is only light, moving steadily, carrying information at a fixed speed, and arriving exactly when it must. Because light does not travel instantly, every observation is delayed. This delay is small for nearby objects and grows larger with distance. The moon is seen as it was a little over 1 second ago. The sun is seen as it was a little over 8 minutes ago. These delays are short enough to feel trivial, yet they already demonstrate the principle. Even the most familiar objects in the sky are never seen exactly as they are right now. Once attention moves beyond the solar system, the effect becomes impossible to ignore. Light from nearby stars takes years to reach Earth. When that light enters a telescope, it brings with it information that has been travelling uninterrupted since before it was detected. The star may have shifted slightly, brightened, dimmed, or changed in ways that have not yet arrived. This does not mean astronomers are guessing about the past. They are observing it directly. The information is real. It is simply old. Starlight carries details about temperature, composition, motion, and structure. Embedded in that light are subtle patterns that scientists can analyze with great precision. By breaking starlight into its component colors, astronomers learn what elements are present in a star, how fast it is moving, and even how its surface behaves. All of this information reflects the state of the star at the moment the light was emitted. The delay involved is not optional. It is built into the universe. No improvement in technology can remove it. Faster telescopes collect more light. Better detectors extract more detail, but none of them can make light arrive sooner than it already has. This is why seeing distance as time is not a poetic choice. It is an observational necessity. A helpful way to approach this is through everyday delays. Imagine sending a message across a large ocean before instant communication existed. Weeks might pass before a reply returned. The response would reflect conditions from the time the message was written, not the moment it was read. No one would confuse this delay with fantasy. It would simply be the cost of distance. Light behaves the same way, just far more reliably. It never gets lost. It never arrives early. It always carries the state of its source from the moment it left. Astronomers often emphasize this point when explaining why the universe appears the way it does. When a distant galaxy is observed, the light reaching Earth may have been traveling for millions or even billions of years. That observation shows the galaxy as it once was, not as it is now. The present state exists, but its light has not yet arrived. This idea can feel unsettling at first, as if the universe was slightly out of sync with itself. In practice, it becomes one of the most powerful tools in science. By observing objects at different distances, astronomers effectively observe different stages of cosmic history. Nearby objects show the universe relatively recently. Distant objects reveal it much earlier. Institutions studying cosmology rely on this layered view constantly. By comparing light from galaxies at varying distances, scientists reconstruct how structures formed and evolved over time. This is not speculation. It is measurement, guided by the predictable behavior of light. There is gentle humor in how the universe insists on patience. Every photon carries a record of its departure time, whether anyone asks for it or not. The farther it travels, the older the story it tells. The universe does not hurry to update its image. Importantly, this does not mean astronomers are blind to the present. They simply understand that the present cannot be observed at great distances. The speed of light sets a limit on immediacy. Beyond that limit, everything becomes historical. This also clarifies a common misunderstanding. Seeing into the past does not mean seeing something that no longer exists. Many stars observed today still shine. Many galaxies continue to evolve. The light arriving now is simply an earlier chapter, not a final one. Scientists are careful to distinguish between what is observed and what is inferred. Models allow them to estimate how objects likely behave now based on physical laws. But direct observation always lags behind reality. That lag is acknowledged rather than ignored. Seeing distance as time also reshapes how events are understood. When a sudden change occurs in a distant object, such as a powerful burst of radiation, it may be detected long after it actually happened. Instruments record the arrival, not the moment of origin. This delay does not reduce the significance of the event, it simply places it correctly in time. This layered arrival of information gives the universe a calm, staggered quality. Everything that happens echoes outward slowly. Nothing announces itself instantly across space. Change spreads at the pace light allows. For human experience, this is unusual. On Earth, most feedback feels immediate. Sounds arrive quickly. Visual cues update constantly. Distance rarely introduces meaningful delay. Space quietly removes that immediacy. There is comfort in this once it is accepted. The universe does not rush information. It releases it gradually. Each observation is part of an ongoing flow rather than a sudden reveal. Astronomers often describe this as reading the universe rather than watching it live. Each beam of light is a sentence written long ago, arriving now. The story unfolds not all at once but page by page, depending on how far one looks. This does not diminish discovery, it deepens it. Knowing that light carries history adds context. It turns observation into connection across time. The idea also dissolves the urge for urgency. If everything seen at great distances is already delayed, then waiting becomes natural. The universe operates on timescales that do not respond to impatience. Understanding distance as time also reinforces why light years are such a useful unit. They describe not just how far something is, but how long its message has been travelling. Distance and delay become inseparable. This perspective encourages a slower way of thinking. Instead of asking how quickly something can be reached, it invites reflection on how long something has been known. It shifts focus from travel to transmission. As this idea settles, the sky begins to feel less like a snapshot and more like a record. Every point of light carries memory. Every observation is a meeting across time. There is no need to rush this understanding. It does not demand excitement or alarm. It simply asks for a small adjustment in how distance is imagined. Looking far away means looking long ago. Light makes that true, quietly and consistently. And once that is accepted, the universe feels less strange, not because it is smaller, but because its rules are finally being followed at their own pace. When the subject turns to light years, confusion often arrives quietly without warning, not because the idea is poorly explained, but because the human brain was never designed to work comfortably at that scale. This resistance is not a flaw. It is a feature of how minds evolved. For most of human history, useful numbers stayed small. A handful of tools, a few days of travel, a short list of people to recognize and remember. The brain became excellent at managing quantities that could be counted on fingers, estimated at a glance, or felt directly through effort. Anything much larger than that was rare and rarely urgent. Large numbers, especially those tied to abstract concepts like distance and space, fall outside this comfort zone. The brain can repeat them, but it struggles to attach meaning. Saying a number like 9.5 trillion kilometers is easy enough. Understanding what that means is another matter entirely. Cognitive scientists studying numerical perception have shown that the brain does not treat all numbers equally. Small numbers are processed almost instantly. Larger ones require symbolic reasoning rather than intuition. Beyond a certain point, the mind stops picturing and starts labeling. The number becomes a word rather than an experience. This is where abstraction enters and where discomfort often follows. A light year is not something that can be walked, driven, or even imagined visually in any satisfying way. It has no edges, no landmarks, no texture. It exists as a relationship between light, time, and space. The brain prefers things it can place somewhere. A light year refuses to sit still. Because of this, the mind looks for shortcuts. It reaches for stories instead of statistics. This preference is not accidental. Stories compress complexity into sequences of cause and effect. They provide direction, tension, and resolution. Numbers, especially very large ones, do none of these things on their own. When someone hears that a nearby star is several light years away, the number does not lodge itself in memory. What sticks instead is the idea that light has been travelling for years. That is a story. It has duration, it has patience, it unfolds. Astronomers understand this instinct well. Despite working with equations, measurements, and data sets, they rarely communicate using raw numbers alone. They rely on models, metaphors, and comparisons not to simplify the science, but to translate it into a form the brain can tolerate. A model is not a toy version of reality. It is a bridge. When astronomers describe stars as isolated islands, or space as mostly empty, they are not being poetic for effect. They're choosing images that preserve relationships while easing cognitive strain. Scientific institutions encourage this approach because it works. Educational material produced by observatories and space agencies consistently uses layered explanations. A concept is introduced gently, revisited from another angle, and reinforced through analogy. This repetition is not redundancy, it is accommodation. The brain also struggles with scale because it lacks feedback. On Earth, misunderstanding distance has consequences. Walk too far and fatigue appears. Misjudge a jump and gravity intervenes. Space offers no such correction. There is no physical sensation attached to a light year. Nothing pushes back. Without feedback, the brain grows uncertain. It tries to compensate by exaggerating or dismissing. Either the distance feels impossibly large, or it collapses into meaninglessness. Neither response is particularly helpful. This is where gentle humour earns its place. There is something relatable about the idea of the brain quietly giving up, nodding politely and moving on. That reaction is common, even among people deeply interested in space. Understanding does not always arrive with clarity. Sometimes it arrives as acceptance. Confusion in this context is not failure. It is a signal that the concept has exceeded intuitive range. Astronomers expect this. They do not design explanations to eliminate confusion entirely, but to keep it from becoming discouraging. Cognitive research shows that repeated exposure to large scales improves familiarity, even if full intuition never develops. The brain may never feel comfortable with light years, but it can learn to recognize their role. Comfort is replaced with familiarity, and that is enough. Another reason the brain pushes back is that large distances resist comparison. On Earth, distance is relative. One place feels far because another feels near. In space, everything beyond the solar system is far in roughly the same way. The gradient disappears, the brain loses its reference points. This lack of contrast makes abstraction harder. Without nearby anchors, scale floats. Astronomers address this by building ladders of distance. Light seconds lead to light minutes. Light minutes lead to light years. Each step prepares the mind for the next. Even then, the brain remains selective. It will often remember the idea that stars are far apart while forgetting the exact figures involved. This selectivity is not laziness. It is efficiency. The brain prioritizes relationships over measurements. Stories excel at preserving relationships. A story about light leaving a star and arriving years later retains meaning even when the number of years fades. That story captures delay, separation, and patience in a way statistics cannot. Astronomers rely on this storytelling instinct when presenting research. Press releases, lectures, and documentaries often frame discoveries as journeys, signals, or messages. These are not distortions, they are translations. The mind also resists abstraction because it prefers agency. Stories have actors, numbers do not. A beam of light travelling through space feels more graspable than a figure with 12 digits. The brain looks for emotion and narrative wherever it can. This preference can be seen even in professional settings. Scientists use visualizations, animations, and conceptual diagrams to supplement equations. These tools are not signs of weakness. They are acknowledgements of how thinking works. It is worth noting that confusion does not disappear with expertise. Even experienced astronomers report moments where scale becomes overwhelming. Familiarity does not eliminate awe. It simply makes it manageable. Reassurance matters here. Feeling lost does not mean the explanation failed. It means the universe exceeded everyday design specifications. The brain is doing exactly what it evolved to do, and then politely stepping back. There's no requirement to hold every detail in mind at once. Understanding cosmic distance is cumulative. Each exposure leaves a trace. Over time, those traces form a stable impression, even if sharp edges remain fuzzy. This is why light years are best understood gradually, not memorized, not conquered, simply revisited. Light humor helps smooth this process. Laughing at the brain's limitations removes pressure. It allows curiosity to persist without demanding mastery. The goal is not to feel small or inadequate, but to feel oriented. Astronomers often describe their work as learning to be comfortable with approximation. Precision matters in calculation, but understanding thrives on proportion. Knowing that something is far enough for light to need years is more useful than knowing the exact count of kilometers. When the brain pushes back, it is asking for context, not retreat. Models provide that context. Metaphors supply handles. Stories create pathways. Over time, the resistance softens. The brain stops trying to picture everything at once and begins to accept layered understanding. Light years become familiar terms, even if they never become fully intuitive. This acceptance is quiet and uncelebrated. There is no moment where the scale suddenly makes sense. Instead, there is a gradual easing. Confusion becomes a companion rather than an obstacle. In that space, learning continues calmly. The brain may never stop pushing back, but it learns to do so gently, and that is enough to keep exploring a universe that does not scale down easily, but does reward patience. Measuring light years in practice sounds, at first, like it should involve enormous instruments and dramatic calculations. In reality, the process begins with something very modest. Comparison. Careful, repeated comparison made patiently over time. Astronomers cannot stretch a ruler from Earth to a star. They cannot send a probe far enough to mark the distance directly. Instead, they rely on how perspective shifts when the observer moves. This method is called parallax, and it is far less intimidating than it sounds. Parallax is something experienced every day without noticing. Hold a finger out at arm's length and look at it first with one eye, then the other. The finger appears to shift slightly against the background. That shift is not the finger moving. It is perspective changing. The brain uses this effect constantly to judge depth. Astronomers use the same idea, but on a much larger scale. Instead of moving an eye, Earth itself does the moving. As Earth orbits the Sun, its position changes over the course of a year. Nearby stars appear to shift slightly against the much more distant background of other stars. That tiny movement contains information about distance. The shift is extremely small. Even for the closest stars, it is barely noticeable. Measuring it requires precision instruments, careful timing, and repeated observation. No single glance is enough. The measurement emerges slowly as data accumulates. This is where patience becomes essential. Astronomers observe the same stars again and again at different points in Earth's orbit. They compare positions, look for patterns, and rule out errors. The distance is not calculated in a dramatic moment. It is inferred gradually through consistency. What matters here is not the mathematics behind the method, but the philosophy of it. Measurement in astronomy is rarely about a single calculation. It is about agreement. Multiple observations must align. Independent instruments must confirm the same result. The universe does not reveal its scale all at once. Scientific institutions that measure stellar distances place enormous emphasis on reliability. Space-based observatories, free from atmospheric distortion, have refined parallax measurements far beyond what was once possible. By observing stars over many years, these missions have produced distance maps of unprecedented accuracy. Even so, parallax has limits. It works best for relatively nearby stars. As distance increases, the apparent shift becomes smaller and smaller until it is lost in uncertainty. At that point, astronomers turn to other indirect methods. These methods build on known relationships. Certain types of stars behave in predictable ways. Their brightness changes in regular patterns. By observing how bright such a star appears from Earth and comparing it to how bright it is known to be, astronomers can estimate how far away it must be. This is not guesswork. It is calibrated against nearer stars whose distances are already well established. Again, the emphasis is on comparison rather than raw calculation. Observations are layered. One method supports another. Each new measurement is anchored to previous ones. The entire system grows outward like a carefully constructed scaffold. This is why trust in accumulated observation is so important. No single astronomer measures a light year alone. The distances used today rest on generations of work. Each improvement in technology refines earlier results rather than discarding them. There is something reassuring about this process. It is slow, deliberate, and self-correcting. Mistakes are not catastrophic. They are identified over time as measurements are repeated and compared. The universe rewards consistency. Gentle humour sometimes appears in how astronomers talk about their work. Measuring distances across space often involves staring at tiny shifts that barely rise above noise. It is not glamorous. It is meticulous. The excitement comes not from sudden discovery, but from quiet confirmation. Light years, then, are not pulled from thin air. They are earned through patience. Each one represents countless hours of observation, careful calibration, and cautious interpretation. The numbers used are not bold guesses. They are conservative conclusions. This careful approach also explains why astronomical distances sometimes change slightly as new data arrives. When instruments improve, measurements sharpen. Distances are refined, not overturned. This is a sign of a healthy science, not uncertainty. Space agencies and observatories openly revise their distance estimates when warranted. Transparency is part of the process. Trust grows when updates are expected rather than hidden. For listeners, this means that light years are not abstract inventions. They are the result of steady, disciplined observation carried out by many people across many decades. Each light year carries with it a history of looking, waiting, and checking again. There is also an important emotional shift here. Measurement becomes less about conquering distance and more about respecting it. The universe is not something to be rushed. It reveals itself at the pace allowed by light and motion. This respect for pace shapes how astronomers work. Observations are planned months or years in advance. Data sets are revisited long after they are collected. Patterns emerge slowly. Confidence grows incrementally. Seeing measurement this way removes pressure. There is no expectation of instant clarity. Uncertainty is allowed to exist while understanding improves. The process mirrors the universe itself, steady and unhurried. Parallax and indirect methods work not because they are clever, but because they are honest. They acknowledge limitations and work within them. They accept that distance cannot be touched directly, only inferred carefully. In this sense, measuring light years is an act of trust. Trust that the rules governing light remain consistent. Trust that repeated observation reveals truth. Trust that small shifts, when seen clearly enough, carry meaning. For those outside astronomy, this can feel counterintuitive. Precision is often associated with speed and certainty. In space, precision grows from patience. The more time given, the more reliable the result. This approach has served science well. It has allowed humanity to build a map of the nearby universe without ever leaving its home planet. That map is not perfect, but it is remarkably consistent. Each measured light year stands as a quiet testament to observation done carefully. No shortcuts, no spectacle, just comparison, repetition, and attention. And in that methodical calm, distance becomes something that can be known, even if it can never be crossed. When distance is measured across an entire galaxy, light years stop being surprising and start becoming practical. At this scale, they are no longer dramatic units reserved for extreme cases. They are simply the most comfortable way to speak. A galaxy is not a compact object. It is not a solid shape filled edge to edge with stars. It is an extended structure, spread thinly across space, held together by gravity but mostly composed of emptiness. When astronomers describe the size of a galaxy, they are describing how far its influence stretches, not how crowded it is. A typical large spiral galaxy spans on the order of 100,000 light-years from one side to the other. That number sounds imposing, but it is best treated as a gentle boundary rather than a solid edge. Stars become less dense toward the outskirts. The galaxy fades rather than ends. Inside this vast span, stars are arranged in patterns. Spiral arms curve outward. A central region holds a denser concentration of stars. Yet even within these structures, space dominates. Stars are separated by light years, not by light minutes or light seconds. They are neighbours only in the loosest sense. This sparseness is often difficult to reconcile with images of galaxies glowing brightly in the sky. Those images compress scale. They gather light over long exposures and flatten 3 dimensions into 2. The result looks crowded. The reality is anything but. If the galaxy were scaled so that each star were the size of a grain of sand, the distance between grains would still be measured in many meters. The space between them would feel empty, quiet, and undisturbed. Structure would exist, but it would be subtle. Galaxies are shaped by gravity acting over immense distances. That gravity does not pull everything together into a dense mass. Instead, it guides motion slowly, allowing stars to orbit common centers while remaining far apart. The result is organization without compression. Astronomers studying galactic structure emphasize this balance. A galaxy is neither chaotic nor crowded. It is arranged but spacious. Patterns emerge not because matter is tightly packed, but because it moves coherently over long time scales. Light years are essential here because no other unit captures this balance as naturally. Kilometers collapse under the weight of scale. Even astronomical units become unwieldy. Light years allow the discussion to stay broad and calm. Within a galaxy, light can travel for tens of thousands of years before crossing from one side to the other. During that time, stars continue their slow orbits. Entire civilizations could rise and disappear on planets around those stars without ever influencing one another. This is not isolation in a dramatic sense. It is simply separation by space. Galaxies are not bustling cities of stars. They are more like sparse archipelagos, with vast distances of open water between islands. Scientific institutions mapping galaxies rely on this understanding constantly. When they chart stellar populations, they do not imagine stars bumping into one another. They track slow movements across light years, measured over decades of observation. The calm scale of a galaxy also explains why collisions between stars are extraordinarily rare. Even in the denser central regions, the average distance between stars remains enormous compared to their size. A galaxy can pass through another galaxy with very few direct stellar encounters. Most stars simply drift past one another, separated by space. This idea often surprises people because the word collision suggests violence. In reality, galactic interactions are mostly quiet. Gravitational influences stretch structures, alter orbits, and reshape patterns over hundreds of millions of years. The stars themselves remain largely untouched. Emphasizing emptiness helps correct another common intuition. Large numbers of stars do not imply closeness. A galaxy can contain hundreds of billions of stars and still be overwhelmingly empty. Quantity does not equal density. Light years help hold this distinction. Saying that two stars are separated by several light years immediately suggests room. It implies time for light to travel. It implies silence between signals. Astronomers avoid overwhelming detail here for good reason. The exact number of stars in a galaxy is less important than how they are spaced. The broad picture carries more meaning than precise counts. Galactic scale also introduces a drifting sense of time. Stars orbit slowly around the galactic center, taking hundreds of millions of years to complete a single circuit. These motions are not hurried. They unfold steadily, guided by gravity and inertia. This slow movement contributes to the calm character of galactic space. Nothing rushes, nothing collides frequently. Change happens, but on timescales that dwarf human history. Light years capture this pace naturally. They are large enough to match the distances involved without forcing attention onto individual figures. They allow the listener to sense scale without becoming lost in it. There is gentle humour in how language adjusts. Phrases like nearby star or local region still apply within a galaxy, even though nearby might mean a few dozen light years. The words remain familiar while their meanings stretch quietly. Galaxies themselves are separated by even larger distances, but within a single galaxy, the same principle holds. Structure exists without crowding. Organization emerges without compression. This understanding reshapes how space is imagined. Instead of a packed environment filled with constant interaction, a galaxy becomes a wide open system where stars move gracefully through vast volumes of emptiness. Astronomers often describe galaxies as ecosystems rather than machines. Each star system evolves largely independently, influenced by the broader gravitational environment, but not constantly disturbed by neighbours. Light years make that independence clear. They emphasize separation while preserving connection. Light travels between stars, carrying information slowly. Gravity links them, but gently. Maintaining a calm, drifting sense of scale is essential here. The goal is not to impress with enormity, but to orient perception. A galaxy is large because space itself is large. That largeness is not aggressive, it is simply present. When light years are used at this scale, they stop feeling exotic. They become the natural language of description. The mind adjusts not by fully grasping the numbers, but by accepting the relationships they represent. A galaxy measured in light years is not a wall of stars. It is a wide field, lightly populated, shaped over immense time. Distance defines its character as much as gravity does. Once this perspective settles, the image of a galaxy changes. It becomes quieter, more spacious, less crowded than imagined. Light years do not compress this view, they preserve it. Across a galaxy, distance is not an obstacle. It is the medium through which structure exists. Stars remain separated, light moves patiently, and the entire system drifts together, unhurried, through an even larger universe. In that gentle drift, scale stops feeling overwhelming. It becomes consistent. A galaxy is large, yes, but it is also calm, and light years are simply the measure that fits. Once attention moves beyond a single galaxy, distance expands again, gently but decisively. Light years that once felt large now become stepping stones. Between galaxies, separation is measured not in thousands of light years, but in millions. This does not mean space suddenly becomes chaotic or overwhelming. It means the same quiet rules continue to apply. simply across broader spans. Galaxies are not packed tightly together. They're arranged in loose patterns, connected by gravity, separated by vast regions where very little happens at all. Intergalactic space is often described as empty, but that word can be misleading. Empty suggests absence. In reality, intergalactic space is more accurately described as thin. Matter exists there, but sparsely. A few atoms drift through volumes that would swallow entire galaxies without notice. Light passes through largely unimpeded, carrying information across immense distances. When astronomers measure the distance between neighbouring galaxies, the figures typically fall in the range of millions of light years. That means light leaving one galaxy must travel for millions of years before reaching the next. During that time, stars are born and die, planetary systems evolve, and entire eras of galactic history unfold independently. These numbers sound large, but they behave in a familiar way. Light still travels at the same steady speed. Time still accumulates. Distance still unfolds patiently. The unit remains useful because the relationship it describes remains unchanged. Light years work at this scale because they are not tied to human movement or convenience. They are tied to light itself, which does not care whether it is crossing a solar system, a galaxy, or the space between galaxies. The same rule applies everywhere. 1 year of light travel is always 1 year of light travel. This consistency is what allows astronomers to speak calmly about enormous distances without resorting to new units or dramatic language. 1,000,000 light years may sound vast, but it is simply a longer journey for light. Nothing else about the universe changes to accommodate it. Intergalactic space also reveals something important about structure. On the larger scales, matter is not scattered randomly. Galaxies tend to form clusters and filaments, leaving wide regions between them that are comparatively empty. This pattern is sometimes called the large-scale structure of the universe. The key word here is structure, not chaos. Space beyond galaxies is not an endless void without form. It has shape, but that shape is subtle. It emerges from gravity acting slowly over immense spans of time. Scientific institutions studying cosmology map these patterns by observing how galaxies are distributed across the sky. They measure distances using light travel time and compare positions across enormous surveys. The result is a picture of the universe that looks less like a uniform fog and more like a delicate network. Within this network, vast spaces exist where few galaxies reside. These regions are not threatening. They're simply quiet. Gravity still operates there. Light still passes through. Nothing dramatic needs to happen for space to exist meaningfully. Avoiding language about infinity helps here. Infinity suggests something unbounded and unknowable. Intergalactic space, while vast, is measurable. Its distances can be estimated. Its structures can be traced. It is large, but it is not undefined. Astronomers are careful about this distinction. They describe the observable universe as having a finite size, limited by how far light has been able to travel since the universe began. Beyond that boundary, discussion shifts from observation to inference. Even then, light remains the guide. Millions of light years sound intimidating until they are reframed as patience rather than enormity. Light has simply been travelling for a very long time. It has not struggled. It has not accelerated. It has not slowed. It has just moved. This reframing allows the size of space to feel spacious rather than threatening. There is room, not pressure. Separation, not confinement. The universe is not closing in. It is opening outward. There is gentle humour in how familiar language stretches here. Neighbouring galaxies are called nearby even though they are millions of light years apart. The word survives, adjusted quietly to a new scale. Meaning follows usage. Light years remain useful at all scales because they describe relationship rather than magnitude. They link distance to time in a way that stays intuitive even as numbers grow. 1,000,000 light years is not a number to memorize. It is 1,000,000 years of travel for light. This way of thinking also keeps attention grounded in observation. Everything known about distant galaxies arrives via light. Their shapes, motions, and histories are encoded in photons that have crossed intergalactic space patiently and reliably. Intergalactic distances also reinforce how little interaction occurs between galaxies on short timescales. While gravity connects them over billions of years, individual stars rarely notice one another across these spans. Each galaxy evolves largely on its own, influenced slowly by its surroundings. This independence adds to the calm character of large-scale space. Nothing is crowded, nothing is rushed. Change happens, but gently. Scientific bodies that study the universe on these scales often emphasize this calm. The universe does not appear hostile or aggressive at its largest extents. It appears ordered, spacious, and surprisingly quiet. Allowing the size to feel spacious rather than threatening requires letting go of urgency. There is no need to grasp every detail at once. Understanding grows by revisiting the idea that light simply keeps going. Beyond galaxies, distance continues to stretch, but the same principles apply. Light travels, time passes, information arrives. The unit does not change. The universe does not raise its voice. It simply becomes wider. In this wider view, light years feel less like a barrier and more like a description of connection across silence. They remind listeners that the universe is not compressed for convenience, but it is consistent in its rules. Space beyond galaxies is not an abyss. It is an extension, structured, quiet, and vast enough to allow countless systems to exist without interference. When distance is allowed to be this spacious, understanding becomes calmer. The universe does not threaten with size, it offers room, and light, moving steadily through it all, continues to provide the measure that makes sense of separation, no matter how far outward the view extends. Light years do more than stretch the imagination. They reach into emotion, quietly rearranging how distance is felt rather than understood. For some, the idea of such vast separation triggers unease. For others, it brings a sense of calm. Often it does both at once. These reactions are not accidental. The human emotional system evolved to respond to environments where distance mattered immediately. A nearby shelter was safety. A distant sound could signal danger. Space measured in steps or seconds carried meaning that could be acted upon. Light years offer no such feedback. They are too large to trigger instinctive responses, yet too real to be dismissed. This mismatch creates emotional ambiguity. The mind understands that something is far away, but the body does not know what to do with that information. There is nothing to flee, nothing to approach. Distance becomes passive, and that passivity can feel unsettling. At the same time, vastness can also be deeply calming. Many people experience a sense of quiet when thinking about space on these scales. The absence of urgency, the slow pace of change, and the sheer room available can reduce the feeling of pressure that comes with more crowded environments. This dual reaction mirrors how people respond to other large, open settings on Earth. Standing at the edge of a desert, for example, can feel intimidating at first. The land stretches outward with no obvious end. There are few landmarks. Movement feels exposed. And yet, after a moment, that same openness can become soothing. The noise fades. The scale absorbs attention rather than demanding it. Deep oceans evoke a similar response. Knowing that water extends for kilometers beneath the surface can feel overwhelming. The depth is real, measurable, and largely inaccessible. Yet for many, the vastness of the ocean also brings calm. Waves repeat. The horizon remains steady. Nothing rushes. Cosmic distance behaves in much the same way. Light years create a sense of exposure to scale without threat. There is no immediate consequence attached to understanding them. They exist as context rather than challenge. Scientists who study perception often note that emotional responses to scale depend on framing. When vastness is presented as something that diminishes importance, it can feel unsettling. When it is presented as something that provides context, it often feels grounding. Light years are particularly effective at shifting perspective because they remove comparison. There is no meaningful way to compete with cosmic distance. This dissolves certain anxieties quietly. The universe is not asking for attention or approval. It simply exists at its own scale. Astronomers are aware of this emotional dimension, even if it is not always discussed explicitly. Public communication from scientific institutions often emphasizes wonder without threat. Images of distant galaxies are presented not as reminders of insignificance, but as invitations to curiosity. This distinction matters. Feeling small is not the same as feeling unimportant. Light years do not erase human experience. They contextualize it. Earth remains the place where life is lived. Cosmic distance does not change that. In fact, perspective can enhance meaning rather than reduce it. Knowing that light has travelled for years or millions of years to reach Earth can make the act of observation feel special rather than trivial. It highlights connection rather than isolation. Emotional reactions also vary depending on how distance is imagined. When light years are thought of as empty space to be crossed, they can feel forbidding. When they are thought of as time already travelled by light, they feel quieter. The journey has already happened. Nothing needs to be done. This framing reduces pressure. There is no expectation to bridge the distance. The universe is not waiting. It is already in motion. Gentle humour sometimes helps ease emotional tension here. The idea that the brain encounters a number so large that it politely excuses itself can be comforting. Confusion becomes a shared experience rather than a personal failing. There is also reassurance in knowing that even experts feel this strangeness. Astronomers may work with light years daily, but they do not experience them viscerally. They rely on models and language precisely because raw intuition does not apply. Light years are emotionally strange because they do not fit into existing categories. They are not distances that invite travel. They are not times that invite anticipation. They sit somewhere between, resisting narrative closure. This resistance can feel uncomfortable, but it can also feel freeing. Without a demand for action, the mind is allowed to rest. Curiosity replaces urgency. Comparisons to deserts and oceans are helpful because they show that humans already have experience with vastness. These environments are not hostile by default. They are simply large. When approached with respect rather than fear, they often inspire calm. Cosmic distance extends that experience beyond Earth. It removes familiar reference points, but it preserves rhythm. Light moves steadily. Gravity acts gently. Structures form slowly. Emphasizing perspective rather than insignificance helps anchor emotional response. The universe is large, yes, but that largeness does not erase human scale. It simply sits alongside it. Earth remains the place where minutes matter, where distances are crossed by walking, driving, and flying. Light years operate elsewhere. They do not compete with daily life. They coexist. Gently returning to the human viewpoint helps resolve emotional tension. One does not need to inhabit cosmic scale to appreciate it. Understanding can remain intellectual, reflective, and calm. Looking up at the night sky, the stars appear close together, scattered across a small patch of darkness. Knowing that they are separated by light years does not change their appearance. It changes interpretation. That change does not have to feel heavy. It can feel expansive. The same sky now carries depth as well as pattern, time as well as light. Light years become emotionally strange not because they threaten meaning, but because they remove familiar anchors. Once new anchors form, such as patience, continuity, and scale, the strangeness softens. There is room in this perspective for reassurance. The universe does not judge. It does not demand. It simply provides context that extends far beyond individual concerns. In that context, human experience gains clarity. Life happens on a small planet, within a narrow range of distances and times. That limitation is not a weakness. It is a condition that allows focus. Cosmic distance does not diminish that focus. It frames it. By the time light years begin to feel emotionally neutral rather than strange, something has shifted quietly. The universe feels less like a challenge and more like a setting. Vastness becomes background rather than threat. Emptiness becomes space rather than absence. Distance becomes time already spent rather than distance still to cross. In that shift, calm often follows. Light years stop feeling overwhelming and start feeling descriptive. They are not there to make anyone feel small. They are there to describe how gently and patiently the universe carries information across space. And once that is understood, the emotional weight lifts. The scale remains large, but the feeling becomes lighter. Astronomers have never relied on a single way to measure space. Long before light years became familiar, other units were already doing careful work. Within the solar system, distances are often expressed in astronomical units, defined as the average distance between Earth and the Sun. This keeps numbers manageable and directly tied to orbital motion. For even smaller scales, kilometers and meters remain perfectly useful. No one insists on using light years to describe the distance to the Moon. At larger scales, other alternatives appear. One commonly used unit in professional astronomy is the parsec. It is based on parallax and defined through observation rather than travel. A parsec corresponds to the distance at which Earth's orbit produces a specific, very small apparent shift in a star's position. In practice, astronomers often think in parsecs when working with measurement techniques, catalogues, and calculations. So why do light years persist? The answer is not tradition for tradition's sake, nor stubbornness. Light years persist because they are practical, communicative, and closely aligned with how astronomy actually works. They connect distance directly to observation. They describe not just how far something is, but how long its information has been travelling. Parsecs are precise and useful within scientific work, but they are abstract in a different way. They are rooted in geometry and observation angles that do not translate easily outside professional contexts. Light years, by contrast, borrow a familiar unit of time and repurpose it gently. A year is something everyone understands. Light provides the motion. The connection forms naturally. This shared understanding matters. Astronomy is not practiced in isolation. Results are communicated across institutions, disciplines, and to the public. Units that carry meaning beyond equations make that communication smoother. Light years offer a common language that preserves accuracy without demanding technical background. Importantly, using light years does not imply uncertainty or compromise. The science underneath is rigorous. Distances expressed in light years are often derived from measurements made in parsecs, calibrated carefully, and cross-checked through multiple methods. The unit used to present the result does not weaken the result itself. Scientific institutions are clear about this distinction. Internal calculations may use one set of units, while public-facing explanations use another. This is not inconsistency, it is translation. There is gentle humour in how this sometimes plays out. Astronomers may happily work through pages of calculations in one unit, then switch to light years when explaining the outcome over coffee. The universe has not changed in the meantime. Only the language has. Light years also scale smoothly. They remain useful from nearby stars all the way to the largest observable structures. A few light years, thousands of light years, millions of light years. The same concept stretches without breaking. No new mental framework is required at each step. This continuity builds confidence. Once the idea of a light year settles in, it does not need to be relearned. It simply expands. Alternatives still have their place. Astronomical units excel within planetary systems. Parsecs are indispensable for measurement techniques and professional catalogues. Kilometers and meters remain essential for engineering and instrumentation. Astronomy does not choose one unit because others failed. It uses many, each where it fits best. Light years persist because they fit naturally at the boundary between measurement and meaning. They also reinforce an important truth. Astronomy is an observational science. Everything known about distant objects arrives via light. Using a unit based on light travel time keeps that reality visible rather than hidden behind abstraction. Maintaining confidence in the method means recognizing that no single unit carries the full story. Light years do not replace careful measurement. They rest on it. In that sense, asking whether light years are the best way to measure space slightly misses the point. They are not the only way. They are the most communicative way when distance becomes truly cosmic, and that is why they remain in use. Not because they are perfect, but because they work. Calmly, consistently, and without fuss. Once light years become familiar, something subtle changes in how the universe is seen. Distance stops being a backdrop and starts becoming an active part of understanding. Scale reshapes interpretation long before it reshapes emotion. In astronomy, distance does not simply determine how far away something is. It determines what can be known, how clearly it can be measured, and how confidently conclusions can be drawn. A nearby object reveals detail. A distant one reveals history. Both are shaped by how long light has been travelling. Light years make this relationship explicit. They tie observation directly to delay. Seeing farther means seeing earlier. That fact influences how astronomers design studies, interpret data, and compare objects across space. When two stars appear similar but lie at very different distances, the comparison changes. One may be seen almost as it is now. The other is seen as it was years ago. Distance becomes context rather than inconvenience. This reshaping of perspective extends beyond individual objects. Entire populations of stars, galaxies, and cosmic structures are understood differently depending on their distance. Light years help organize these differences without forcing them into a single frame. Scale also influences expectation. Close objects are studied for detail. Distant ones are studied for pattern. This is not a limitation of technology. It is a consequence of light travel time and signal strength. Astronomers account for this constantly. Observational strategies are chosen based on distance. Instruments are tuned to capture faint signals from faraway sources, knowing that those signals represent earlier stages of cosmic evolution. Light years quietly sit at the center of this planning. They inform exposure times, data interpretation, and comparison across surveys. Distance is not just a number in a catalogue. It is a parameter that shapes the entire approach. Tying light, time, and space together gently avoids philosophical overreach. There is no need to turn distance into metaphor. The relationship is physical and measurable. Light moves, time passes, space separates, yet insight still emerges. Once distance is understood this way, the universe feels less static. It becomes layered. Nearby space represents recent conditions. Farther space represents earlier ones. The sky becomes a record rather than a snapshot. This does not require awe to be meaningful. It requires consistency. Light years provide that consistency by linking every observation to a clear temporal context. Scientific bodies studying cosmology rely on this link when reconstructing how the universe evolved. By observing objects at increasing distances, they effectively sample different eras. This is not speculation. It is the natural outcome of finite light speed. Distance also influences confidence. Astronomers speak differently about nearby objects than about very distant ones, not because the science weakens, but because the information arrives with different constraints. Light years help signal those constraints clearly. What changes ultimately is not just what is seen, but how it is interpreted. Scale shapes questions. It determines what kinds of answers are possible. Light years also encourage patience. They remind observers that the universe does not deliver information instantly. Understanding accumulates over time, just as light does. This perspective carries a quiet reassurance. Nothing important is being missed in the moment. The universe unfolds at a pace set by its own rules, and those rules are consistent everywhere. Letting insight feel earned rather than forced allows it to settle naturally. There is no sudden revelation where everything clicks. Instead, understanding deepens gradually as relationships become familiar. Light years do not explain everything. They do not need to. They provide structure. They organize experience. They connect observation to reality without drama. By the time this way of seeing settles in, the universe feels less abstract. Distance is no longer an obstacle to comprehension. It is part of the explanation. Light years change how the universe is seen by making time visible within space. They remind observers that every point of light has travelled, waited, and arrived. That reminder does not overwhelm. It steadies. The universe becomes a place where distance has meaning, where scale guides understanding, and where light quietly carries information across vast separation without hurry. And in that steady movement, astronomy finds its rhythm. Living in a universe measured in light years changes very little about daily life, and yet it quietly reshapes perspective. The distances themselves do not intrude. They do not demand attention. They simply exist in the background, providing a steady framework for understanding where things are, when information arrives, and how patiently the universe unfolds. Light years act as a quiet organizing principle. They do not describe movement or ambition. They describe relationship, how far apart things are, how long light has been traveling, how separation and time intertwine without hurry. This way of measuring space emphasizes stability rather than drama. When distances are counted in years of light travel, sudden change becomes rare. Most things in the universe move slowly. Stars orbit gently. Galaxies drift gradually. Structures persist for millions or billions of years with only subtle alteration. Astronomers often point out that the night sky appears calm because it truly is. Even when events occur that release enormous amounts of energy, the scale of space absorbs them. Their influence spreads outward at the speed of light, thinning as it goes. Vast distance acts as a buffer, not a threat. This is why immense separation does not imply chaos. Quite the opposite. Distance allows order to exist without constant interference. Stars form, evolve, and age without colliding frequently. Planetary systems remain stable for long stretches of time. Galaxies maintain structure over spans that dwarf human history. Light years help make this stability visible. They remind observers that change takes time to arrive, that most of what is seen has been steady for longer than memory, that the universe is not constantly rearranging itself at random. Scientific bodies studying cosmic evolution consistently find this calm underlying pattern. While the universe does expand and structures do change, they do so according to well-understood physical principles. Gravity acts predictably. Light travels reliably. Large-scale order emerges naturally from simple rules applied patiently over time. From this perspective, vastness becomes reassuring. There is room for systems to exist without crowding. There is time for processes to unfold fully. Nothing needs to rush. Living with this understanding does not require constant awareness of scale. It simply removes the expectation that everything must be immediate. Messages take time. Influence spreads gradually. Observation arrives delayed but intact. This can subtly affect how uncertainty is felt. When the universe is understood to operate over long timescales, not every unanswered question feels urgent. Some things are still on their way. Some information has not arrived yet. Waiting becomes part of the structure rather than a failure of knowledge. There is gentle humour in how small human impatience appears against this backdrop. Wanting instant clarity in a universe measured by light years is a bit like wanting a continent to rearrange itself overnight. The mismatch is not tragic. It is simply human. Light years also encourage trust in continuity. The same physical laws apply everywhere. Light behaves the same whether it is crossing a laboratory, a solar system, or the space between galaxies. This consistency anchors understanding. Distance does not introduce unpredictability. It introduces delay. Astronomers rely on this trust constantly. When they observe distant objects, they are confident that the light has followed the same rules from start to finish. That confidence allows them to reconstruct events that occurred long ago, even across vast separations. For listeners, this can bring a sense of calm. The universe is not fragile. It does not teeter on the edge of disorder. Its scale is large precisely because its rules are stable enough to sustain it. Reframing light years this way also softens emotional response. Distance stops feeling like isolation and starts feeling like spacing. Systems are not alone because something went wrong. They are spaced because space itself is abundant. This abundance creates quiet boundaries. It limits interference. It allows complexity to develop independently. It gives the universe its layered character, where different regions evolve at their own pace. As attention begins to turn toward closure, this perspective settles naturally. The question of how far a light year is no longer feels pressing. The answer is unfolded gradually, not as a number, but as a way of seeing. Light years have revealed that distance is not merely about separation. It is about timing, about patience, about understanding that observation arrives when it arrives, neither early nor late. Living in a universe measured this way does not require awe to be meaningful. Awe can be fleeting. Stability endures. The stars overhead continue to shine, their light continues to travel, the delays remain constant. Nothing about this arrangement is hurried or precarious. Even the expansion of the universe, often described in dramatic terms, unfolds steadily over billions of years. Galaxies drift apart slowly. Structures evolve gently. Vast distance stretches without tearing the fabric of reality. This long view encourages a softer relationship with scale. There is no need to grasp everything at once. Understanding can remain partial and still be accurate. Light years provide orientation, not total comprehension. From a human perspective, this is comforting. Life unfolds on a planet where distances are measured in steps and minutes. Those scales remain valid and meaningful. Light years operate elsewhere, providing context rather than competition. Nothing about cosmic distance diminishes local experience, it simply frames it. Earth remains a place of immediacy, connection, and detail. The universe beyond remains a place of patience, structure, and continuity. As these ideas settle, the universe feels less abstract. Not smaller, but steadier. Not threatening, but expansive. Light years stop being something to struggle with. They become something to lean on. a quiet reminder that separation does not imply disorder, and that time and space work together calmly across unimaginable spans. Living in a universe measured this way means accepting that not everything is instant, and not everything needs to be. It means recognizing that understanding arrives gradually, just as light does. The distances remain vast, the scales remain large, but the feeling shifts. Instead of awe pressing in, there is room to breathe. The universe stretches outward patiently. Light continues its steady journey. And within that vast, ordered space, there is a sense of place that does not require urgency or resolution. Measured in light years, the universe is not chaotic. It is composed, stable, quietly immense, and living within it, understanding that scale can feel less like standing at the edge of something overwhelming, and more like resting inside something enduring. How far is a light year really? By now the question feels less like something that demands a number, and more like something that invites perspective. A light year has revealed itself not as a distance meant to be memorized, but as a relationship between light and time, between separation and patience, between where something is and when it can be known. Understanding it never required holding the full scale in the mind all at once. That was never the goal. What matters is recognizing how the pieces fit together. Light moves at a steady pace. Time passes. Distance accumulates. The universe measures itself quietly through that motion, whether anyone is counting or not. A light year is large, but largeness alone is not the point. What gives it meaning is context. Within the solar system, light seconds and light minutes make sense. Between stars, light years become natural. Between galaxies, millions of light years remain useful without becoming abstract. Distance shifts its language depending on where it is used. This flexibility is reassuring. It shows that scale is not something fixed and intimidating, but something relational. Near and far only exist in comparison. What feels immense in one setting feels ordinary in another. The universe does not insist on a single frame of reference. It also becomes clear that understanding does not require full comprehension. No one needs to picture a light year in detail to use it meaningfully. Astronomers do not hold the entire universe in their heads. They work with layers, with approximations, with trust in consistency. That same approach works here. Understanding grows by revisiting the idea gently, letting it settle without pressure. Confusion is not a sign of failure. It is a sign that the scale being considered exceeds everyday design limits. Distance, seen this way, stops being something absolute. It becomes a relationship between observer and signal, between event and arrival, between now and then. Light years describe not just where something is, but how long its story has been travelling. This perspective removes urgency. There is no requirement to resolve everything immediately. Some information is still on its way. Some light has not yet arrived. The universe unfolds on timescales that do not respond to impatience. That is not a limitation. It is a feature. The night sky does not rush to explain itself. Stars shine steadily. Galaxies drift slowly. Light continues its journey without pause. Distance remains, not as an obstacle, but as part of the structure that allows stability to exist at all. When distance is understood as contextual and relational, it loses its edge. It no longer threatens to overwhelm. It simply describes how space and time cooperate. And in that cooperation, there is calm. The universe measured in light years is not chaotic or hurried. It is spacious, consistent, and patient. Its largest distances are sustained by its most reliable rules. Understanding can follow the same rhythm. There's no need to force clarity where clarity is not required. Insight arrives gradually, just as light does. Each idea reaches the mind in its own time, carrying what it can without urgency. So how far is a light year really? Far enough that light must travel patiently, close enough that its message still arrives, measured not to impress, but to orient. And once that settles, the question no longer presses for an answer. It becomes a quiet companion, reminding us that the universe does not hurry, and understanding does not need to either.